So yeah, we have done some experiments on congestion control for RTP over QUIC. And first, the overall goal of our experiments was not to come up with a perfect solution for doing real-time media over QUIC, but instead to try out different settings for some of the congestion control parameters we can set, and trying out to set these and then see how the connection behaves after we set different configurations for different schemes of congestion control at different layers. For that, we're using RTP, the real-time transport protocol, to transport video stream over QUIC. And RTP has the RTCP protocol, which is the real-time, the RTP control protocol. And we're using a simple encapsulation for carrying RTP and RTCP over QUIC. We use the unreliable datagram extension from QUIC instead of the streams, which were used by default. And to encapsulate our RTP and RTCP packets in QUIC datagrams, we use a very simple encapsulation shown in the picture in the bottom here, where we first have a QUIC package starting with a QUIC header. And then there's a datagram frame following, and we use a flow ID to identify different flows of data, for example, different RTP flows or even other kinds of flows at the receiver. I think it's important to say for datagrams that they are not retransmitted on loss, or they're also not flow controlled, but they are still acknowledged and still subject to congestion control. Then here's a little overview of our overall setup. First, we have an encoder in the top left in red, which produces the encoded media stream and passes it on to some application, which then puts the data into RTP packets and passes them onto our RTP over QUIC implementation. There we add the flow identifier I mentioned earlier, and then we send the packets as QUIC datagrams to the receiver. And we have some interface requirements on the QUIC implementations and on the congestion control controller in our setup, which are that the QUIC implementation has to provide AG and loss signaling for datagrams to our RTP over QUIC implementation. And the congestion controller must be able to produce bandwidth estimation, which we can use for our media encoder using the inputs provided by the QUIC implementation, like the datagram acknowledgements and RTT statistics. And the congestion controller can optionally also use things like explicit congestion notifications, for example, to improve the bandwidth estimation. So now we have congestion control in QUIC already. QUIC specifies congestion control algorithms similar to TCP New-Reno, but QUIC does not mandate any algorithm to be used by the sender. So given the statistics we have from a QUIC connection, which are implemented in QUIC and provided to the sender, we can also implement other algorithms than TCP New-Reno, and there are currently different algorithms in investigation in different implementations, for example, QUIC and BBR. And these statistics which can be used to implement different algorithms are, for example, RTT in different forms or acknowledgements from the QUIC packets. RTP itself also provides its own congestion control. Here we have an additional requirement for congestion control, which means that we need to have our data transmitted at very low latency while still providing a useful bandwidth. And loss-based algorithms such as New-Reno may not always be applicable to this requirement, because these algorithms work by filling and draining queues on the network path, which can lead to high delays or at least high delay variations. And this does not work well together with the interactive requirement of low delays. And so we need some algorithms which are based on delay or delay variations. And we already have some of these algorithms given by our MCAT, which are Scream and NADA. These were proposed by the RMCAT working group in the IETF. And then there's also Google Congestion Control, which is published by Google, and I think it's famously used in libwebRTC. And all these algorithms use some form of the delay variations, which are signaled back from the receiver to the sender to provide a bandwidth estimation to the sender to configure the media encoder. And to signal this information back to the sender, they use RTCP, which I mentioned in the beginning already, which can be used for providing this congestion signaling, or also for doing other exchanging other connection statistics between peers using RTP. And in our case, we need something to signal acknowledgements or arrival timestamps of RTP packets to the sender in RTCP. And for that, we can use, for example, RFC 8888, which specifies an RTCP format for exactly these kinds of data. Now that we have different congestion control loops at different layers, we have QUIC congestion control and we also have RTP congestion control. We asked ourselves, what can we do to do congestion control for interactive real-time media when sending it over QUIC, where QUIC has its own congestion control and RTP has its own congestion control. And for that, we tried out different schemes of congestion control setups. The first one was to use only the QUIC congestion control, so only Neureno in our case. And we will ignore this, the results of this experiment later, because I already said that Neureno is not very good for using for sending real-time media because of the filling and draining queues behavior. And then the second experiment we did is to disable the QUIC congestion control, and we only use RTP congestion control, where we used Scream in our experiments. And then the third setup we used is to enable both RTP congestion control on top of QUIC congestion control, which might be useful, for example, when we want to send real-time media over QUIC and at the same time use the same QUIC connection for sending other kinds of data, for example, in streams. And in that case, we want something like overall limit given by QUIC, and then share this limit between the different flows on the connection. And some part of that should go to the RTP flow. Then a second question we asked ourselves when implementing this is, when we already have the QUIC connection statistics I explained earlier, and we also have RTCP, can we somehow use the QUIC connection statistics to reduce the overhead produced by RTCP? And for that, we did another experiment where we built a small, simple algorithm to build the RTCP feedback on the sender side, only using the QUIC connection statistics. And for that, we record each outgoing RTP packet and take a timestamp of when it was sent. And then we try to get the datagram acknowledgements, which I explained earlier in the QUIC interface requirements, and the RTT statistics from QUIC. And we estimate the receive timestamp, which would usually be given in the RTCP packets, by calculating the receive timestamp as send timestamp plus latest RTT divided by 2. This has already been pointed out for this calculation that it is very simple, and that it is not taking into account that the return path of the connection may not be congested. And so it might have some downside and might use some optimizations, and we will get back to that in the results section for this experiment later. So here's an overview of our implementation and testbed setup. So first we have on the left side a sender, which reads some video from a raw video file and encodes it using a GStreamer pipeline. The GStreamer pipeline is then integrated with a Scream implementation and the QUIC Go implementation. And we use GStreamer to encode and packetize it into RTP packets, push the RTP packets to our Scream sender, which can log the outgoing packets, and then pass the RTP packets on to the QUIC Go implementation, which sends it to the receiver side on the right here in green again, QUIC Go, receiving the packets, stripping off the flow identifier from the datagram, and pass it on to the Scream receiver, And the receiver then logs the incoming timestamps. And in case of our experiments using RTCP, it provides the feedback which will be sent back via QUIC again in QUIC datagrams. And the RTP packet is then passed on to the GStreamer pipeline to depacketize and decode the media, and then stored in a raw video file again. And to evaluate our experiments using this application, we run both applications in Docker containers, and we apply different network conditions to the virtual interfaces in these Docker containers. We use a bandwidth limit of 1 megabit per second, and we reduce this bandwidth limit to 500 kilobit per second after 60 seconds of a video transmission. And after 90 seconds, we increase it back to 1 megabit for the rest of it, for the rest of the video transmission, which is 2 minutes in total. And we do this reduction to see how the congestion control setup reacts to these different changing link capacities. And then we also run our experiments in different one-way delay settings. And both applications then log their incoming and outcoming RTP and RTCP flows and connect congestion control statistics. And in the end, we use these statistics to analyze our results. And also we look at the video quality analysis, which we can do between the raw video input file and the raw video output file using video quality analysis like PSNR and SSIM. So here's the first result of our experiments using RTP over QUIC compared to RTP over UDP and only using Scream as the congestion control. So QUIC congestion control in this case is disabled. In general, we can see that they have quite similar performance, but it is also notable that the congestion control in Scream, the target bitrate computed by Scream for RTP over QUIC stays slightly lower than the one computed for UDP. And we still have to do some more investigation on why this is happening, but one of the reasons probably is the additional overhead of packet overhead due to the QUIC header and the flow identifier, which needs to be packed in the UDP packet compared to RTP over UDP, where we can just put the whole packet into the one UDP datagram. Then the next results for running Scream and Neureno at the same time. Again, we can see that the target bitrate computed by Scream behaves quite similar to the one in the previous result in the beginning. This is because the Neureno congestion controller in this case stays application limited, so it does not reduce our bandwidth in any way. And we are not using the full congestion window of the Neureno congestion control, and thus the Scream can basically do its thing until we reduce the bandwidth in half after about 1 minute. And in that case, we see both congestion controllers try to adapt to the new link environment, and both try to react on that. And we see that the target bitrate in Scream in that case drops to almost 0 and does not seem to ramp up again in the end. We have tried different one-way delay settings, and sometimes we can see that it ramps up very late again, but we did not further investigate how long it takes until it ramps up again, because the situation is already not usable and we need something better, a better reaction to the bit bandwidth reduction in the beginning. And it doesn't matter how long it takes until it ramps up again, as long as it drops like this, we need something better to react earlier. Then our results on trying to reduce RTCP. Here again, we can see on the left side, Scream target bitrate for experiments using RTCP feedback explicitly sent via QUIC datagrams. And on the right side, we see the results of the target bitrate for congestion feedback only created by QUIC connection statistics. And again, we can see that the bitrate behaves quite similar. So that's a good first sign for us that we can use the QUIC connection statistics. but in this case, we see the experiment at 50 milliseconds one-way delay. And then here in this slide, we can see it at 150 milliseconds. And this is something we've seen in some of these experiments. This is just one example that we see the bitrate drop at some point. In this case, it happens at the very beginning and then takes longer to ramp up when we use the quick connection statistics as compared to the RTCP feedback. And yeah, this is an indication that our calculation is not precise enough to do the feedback just from the RTCP, just from the quick connection statistics. And one thing that we can improve here is what I've already mentioned earlier, a better timestamp estimation than the one which does not take into account that the backward path may not be congested. And then another thing which may have an impact on this is that the quick acknowledgements we are using for this, they may be aggregated or they may even be delayed in some implementations. And due to that, it can happen that we generate our feedback at a time where an acknowledgement from QUIC has not yet arrived, containing an acknowledgement for an RTP packet, which has actually arrived at the receiver. But this acknowledgement does not arrive yet because it will come with the next aggregated acknowledgement or something like that, or a delayed acknowledgement. And then this acknowledgement from QUIC will not be included in our RTCP feedback generated at the sender. And then we will kind of lose a RTP acknowledgement. And this may also lead to reduced performance in this case. Then a quick note on prioritization. We also tried to run all our experiments while sending data in the background on a quick stream next to the RTP flows on the datagrams. But what we have seen is that in our cases, the real-time flows degraded very quickly due to our internal implementation. And that shows that we probably need some prioritization here. The test cases were probably a bit too artificial because we are just constantly sending random data in the background on some stream. And in the real world, we will probably something which looks more like occasional HTTP requests and not constant stream of a lot of data in the background. But still, we will need some case or some form of prioritization. And our current work includes that we try to improve this prioritization in our implementation by first come up with a way to strictly prioritize our real-time flows. And that will probably lead to the opposite situation where we only send real-time data and degrade the other flows in the background. And then our plan is to assign different shares of the overall network, as I said in the beginning, to the real-time and other kinds of flows, or can even come up with some more sophisticated way of assigning shares to different kinds of flows. Yeah, with that, I come to our conclusion. So the main takeaways of our experiments are that having two congestion control loops at transport and media level may be problematic, especially as in our case, we're using Ureno for the loop at the quick connection layer. Then the second point is that it seems to be usable, to be possible to use the quick connection state to reduce RTCP feedback, but we probably need some improvement or optimization to our algorithm here. And one improvement could be a relatively recent draft in the IETF, which adds receive timestamps to acknowledgements. And that would make our calculation obsolete because we can just directly use the receive timestamps, which would then be provided by the quick connection and the quick acknowledgements in ACK frames. And yeah, then the third point, the one I said at last, is that we probably need some prioritization in the future. And we're currently working on extending our testbed to add more test scenarios than just the first simple one, probably also adding different senders or on the same connection to share to share one link between different connections and add different congestion control schemes. And then we of course also want to come up with some prioritization, first a simple one, and then try to give different shares to different flows on the same connection. Yeah, thank you very much for your attention, and I'm happy to answer any questions.
Thank you very much for that. Again, very interesting presentation. How should I pronounce your name? Mattis? Mattis?
Mattis.
Mattis. Okay. So thank you, Mattis. I found it very interesting. I'm first going to go to a question in the chat from DL. Very mysterious nickname, DL. He or she asks, why in slide 10, I think, does the target rate remain very low? Is it a problem with the large RGT?
Yeah, after the bandwidth is reduced, both congestion controllers try to react on that, and the Neutrino congestion control will try to reduce what we are sending, and then the screen congestion controller on top of that will react on that too. And this activity between the two congestion control loops probably leads to bad results in the screen congestion controller, which then is not able to produce a valuable bandwidth anymore, I think, or target bit rate anymore.
Does that answer your question, DL? Please let us know. In the meantime, I had a question on slide 13 about the prioritization. Because we have been discussing this, if we need prioritization for datagrams and how that would work. There is even a proposal that Lucas has posted in the chat. So it would be very useful, I think, if you and your other collaborators could look at that and give some input at the IETF as well. For now, what I was wondering if you, how many datagram streams, they're not really streams, but how many datagram contexts do you have here? Is that like one for video, one for audio, or do you have multiple?
We're only using one for video currently.
Just one for video, right? Because then you could assign that a single priority,
yeah,
probably, and take that into account with the reliable streams.
Yeah,
in that way,
exactly. We can. We want in the future. We probably want to take the overall limit we have by QUIC and then assign different shares to different real-time flows and also other flows. And in our case, that would just be one video flow right now, but there could of course be audio and video flow and different other flows.
Yeah. So it's good. Like I said again, please join the conversation at the IETF. I think we're very interested in hearing about people with some experience with datagram prioritization. Then DL says in the chat that they were expecting Neutrino to react quicker. And they also say their name is Dino Lopez. Okay, I don't think that's a follow-up question. Then we had questions from Vidi. Vidi, if you want, you can unmute and ask them.
Thank you, Robin. Thank you, Mattis. I also think that on slide number 10, if we can go back to the slide, did you measure the congestion window in parallel, like what was going on? I wouldn't expect Reno to just not increase. If this is the case, it might just do, like.
So in the beginning, Neutrino does not increase. Yeah, that's when we are application limited, and I'm not sure how exactly it looks anymore when it's reduced. But I can look that up, I think.
Okay, it would be good to plot the congestion window and some, transport layer things, and you can use QLog probably to do that, and yeah, just to compare what's going on there, because it could be a bug, right? Because it shouldn't look like this. The thing, next question I wanted to ask was, if you go to the conclusion slide, the last one. So do you think, in the paper, it seemed like it was a bit different from the first takeaway, where in the paper it was said that the two were having two congestion controller loops looks promising, but right now you say it's problematic, and I agree with this conclusion better. So do you think running without QUIC congestion controller is the way to go, and just run the Scream or any RTP congestion controller?
I think it depends on which layer you do congestion control, because when we want to send real-time data and other data, that's probably more complicated than when we just want to send real-time flows. And in the case of only sending real-time flows, I think it might be easier to just use real-time congestion control without any QUIC layer congestion control, or replacing the QUIC layer congestion control by that. But as soon as we want to have different shares assigned to different kinds of flows, I think it will be more complicated.
Yeah, even, I mean, I was thinking about this just now. So even, let's say there's one connection, there's reliable stream, and then there's datagram for video audio. I mean, if the spec currently doesn't allow us to, not control a particular stream, but for example, let's assume this audio video datagram is allowed to not, it's allowed to send data even if the congestion controller like Reno doesn't permit it. So if we go with that assumption, I think it should still work, because the stream congestion controller should react to the network bandwidth or changes in the network bandwidth when a new QUIC stream is added. Unless you think that the real-time congestion controllers don't adapt to the changes in the network as fast as the transport layer congestion controllers. So do you have thoughts on that?
I'm not sure what exactly you mean.
Maybe I said a lot. So let me just say it like this. Maybe I can just make it a little simpler. So let's say you have a connection, you have a stream where you are running the Reno congestion controller, and then you have a datagram where you're not permitting any, like you don't stop sending if basically you're not using QUIC congestion controller for this audio video datagram. You're only using RTP. So the RTP congestion controller should react to any changes in the network bandwidth due to this additional stream added in the QUIC connection, right?
Yeah.
Like it should react to that. So there is no need really to run a second congestion controller for the audio video stream. It can just.
I agree that that's another option which we haven't tested in our experiments, that we use, for example, New Reno only for the non-real-time streams and Scream only for the real-time flows. That's true.
Yeah. I'm not like 100% sure that's going to work, but based on
I think it's another option we should add to our extended testbed, maybe, that we try to use New Reno and Scream in the same connection, but not in the way we used it in this experiment, where we use them on top of each other. But then we use it, like you say, like to use New Reno only for the reliable streams, for example, and Scream only for datagrams, which carry real-time data. And then we should see them hopefully react to, like, we would probably also see in non-QUIC connections where we send concurrent streams of data, I think.
Yeah, it's right now it's going to be not allowed to do that, right? Because you use a stack, you have to do something else to disable congestion controller for RTP. But it's something, I don't know. I think about this and I don't know if that's the right way to go.
Well, I think it's definitely worth trying out what happens in our experiments to see how streams and the datagram flows react to that.
Okay, thank you. Thanks a lot. Thanks a lot for the presentation. It's really a very nice presentation and a very interesting topic. And I know you've been probably in touch with IETF MOQ mailing list, and it's good work. Thank you.
Yeah, thank you too for your input.
All right, great. We have several additional comments in the chat on this as well. I think Magnus says that. I'm just going to read it. The challenge with media encoding is how you actually attempt to push and not be application bandwidth limited in relation to Reno with bulk transmission that always has data to send. So here you will starve Reno. That reads more like a comment than a question. And then Guillaume says, again for the slide 10, he is asking how the interaction between the two congestion controllers can lead to a complete starvation if there is no loss or delay on the link.
Well, I think since we're running Scream on top of Neureno, I think that even though there's no real loss or delay variation on the link, it might look to Scream that there is, because the data which goes out of Scream then goes into a queue in Neureno, and Neureno tries to find the link capacity, and that leads to variations in the data sent out of QUIC. And then Scream on top of that will see these variations and think the link is congested and reduce the bit rate like this.
Right. I hope that answers your question, Guillaume. If not, please ask follow-up or unmute and ask follow-up directly. That's also fine. Right now.
Yes, I mean, if I can, okay, I can understand, I clearly understand what you say. Okay, the combination of the two congestion control can be detrimental, but I was wondering why. I mean, it can last 1 minute. I mean, at some points, I mean, I don't remember your RTT, but I suspect at some points, I mean, the congestion control should react and give more bandwidth to the underlying connection or the applications. Okay, maybe it's not so important at this moment, but it is puzzling.
So another work today that has clear future future avenues for exploration. One of them is also in a chat where there's a bit of a discussion to say that you do want to disable the QUIC congestion controller or replace it with something custom for something like RTP. You also need API support for that in the different
of course, yeah, APIs,
applications. And currently there aren't really any of those APIs available for most of the big stacks. So that's also an interesting point to keep into account. Something that I feel we often ignore as academics is those kind of practical implications to things. But also things that we as academics, I think, can give some concrete feedback on to the actual implementation developers to let them know what would be useful.